Okay, I made a video on this and I've realised there was a mistake in one of the parts of the calculation, so I'm going to go back and rework this question again with a slightly better graph. Graphs going into it all the way through. So what we've got is we've got a shunting train. It moves backwards and forwards along a track, moving things backwards and forwards. The story we've got is it starts off at a point, it accelerates over 3 minutes to a known speed of 0.6 kilometers an hour. So we can put 0.6 kilometers per hour at the end of 3 minutes. It stays at a uniform velocity for 2 minutes, and then it brakes where it instantly comes to rest after 4 minutes. So this is this point. So I'm going to label this up and we'll put bits underneath as we need to. So first of all, this part is the initial acceleration. This region is constant speed. Bit up to 9, this is actual braking. Train is slowing down at the moment and comes to rest, so it stops. But continues then to accelerate backwards. So this is a reverse acceleration. So we've got reverse acceleration for 3 minutes. So after 12 minutes it gets to this speed. This is where I made the error and miscalculated what this final speed was. After that time, then for the next 3 minutes after this section, it brakes again. And the first thing to notice on this is that this section is the same area as that section. This is braking and then this is accelerating backwards and then it brakes at the same rate afterwards. So these two slopes are actually just negative versions of each other. So let's do a quick sketch and put in what happens with the acceleration. So we've got acceleration, constant speed is 0 braking. I'll quickly dot this in. So there's going to be some acceleration. And to do that over 3 minutes, that must be 0.2. 0 for that one. And then we've got to work out over for 0.6 over 4 minutes to decelerate. So this is my first little calculation I've got to do. So phase 3, deceleration or braking. So the acceleration is minus 0.6 in 4 minutes, which is minus 0.15. It continues doing that until it gets to this speed down here. So in section 4, we get a speed out. So section 4, accelerate backwards. At minus 0.15, so it's continuing with the same acceleration. So the V at that point is going to be minus 0.15. So all of this part in green here should be minus 1.5 all the way through, and then times 3. Nope. Didn't that not pick up red? Times 3. So my velocity backwards at this point is minus 0.45 kilometers per minute. And this was kilometers per minute squared. So this is a minus 0.45. So I'm going to bring in the better version of the graph. With those values on those bits of graph put in. And let's put in everything we can. So we now know this is minus 0.45. No, this is 0.6. We know all the timings. These are zeros, velocities, and we've got 0.6 here. Sorry, 0.2 on that one, minus 0.15 and 0.15. So we've got acceleration in green, and we've got velocity in red, time in minutes. So now we're going to try and work out what distance does it cover. Now, we've got two forms of distance to think about. There's the distance travelled, and that ignores all direction. So that effectively this triangle goes over the top if we're calculating distance. So we'll do that one first. So sections 1, 2 and 3. We need to know that distance from there to there. So that's a distance covered by doing a trapezium roll. So it's a half. The height of this part in the graph is 0.6. The time is from 5 to 3 on the top, so that's 2. And 9 at the bottom. And this gives me overall, it covers 3.3 kilometres on this first section. Second section, the 4 and the 5, as you could use a trapezium rule with a 0, but it's a triangle. So what's the area under the velocity graph? We now know this is minus 0.145, and the time it took was 6. So that gives me a total distance covered on that section of 1.35 kilometres. So what we can actually do is, first of all, the distance travelled is the sum of them. And that gives me 4.65 kilometres. If I want to know the average speed, notice average speed. It is the distance travelled, not displacement. So the distance travelled, 4.65 divided by 15 minutes. That's how long it took to do that amount of distance. And that gives me 0.31 kilometres per hour, per minute. If I was asked to do this in kilometres per hour, so I can convert it, 0.31 kilometres min, so min hour, so 1 hour, 60 minutes, multiplied by 60, and we get 18.6 kilometres per hour. What about the displacement? Where does it finish? So to find where it finishes, we want the displacement. So what's been happening is we've gone away from the station, and we keep going away from the station, and we keep going away from the station and stop. Then we start coming back towards the station, getting quicker and quicker and quicker. Back towards the station, braking, braking, braking. But this is not necessarily back at the station. This is not where we started, because this is a velocity graph. So we finishes is a displacement, and that needs to change, and that's the difference between these two. So our final displacement S as a displacement is the 3.3 away, subtract the 1.35 we came back. So the 3.3, which is the area under here, minus this 1.35. And that gives me 1.95 kilometres away. Now to check that, I did do a graph online, but we need to think about what does this graph look like as I change it now into a displacement. So we ignore the green bit, we're just looking at the velocity, so I'll put in the original graph again. And let's do the analysis of that velocity, and then we'll check it what Desmos gave me out at the end. So what we need from this is all the way from here, on the way out we get to a maximum distance away of 3.3 kilometres. 3.3, 3.3, that's where we're getting to. In this phase we've got a straight line, and in these phases we've got an acceleration. So an acceleration starts off slow and gets steeper and steeper and steeper. This part is going to be a straight line, and then from that point it shadows off to get to 0 again. So we know the graph here, where it's immediately stationary, should be 0. So you could calculate the actual distance here. So 0.6 times half 0.3 times 3, 0.9. So let's do that part. So phase 1, S equals a half times the velocity at the end, which is 0.6, times the time needed, 3, and this gives me 0.9 kilometres. It's a 0.9 kilometres, so we can put that point in, and it's smoothly curved to come up to that point. We've done 0.6 all that time. Now that should be the same line, but I want to check how much further do we do from that time. So it's 0.6 times the area, so it's the height, times 2. It does a further 1.2 kilometres now at that speed. A further 1.2. So from there to about here. So we should get up to about there. And notice the gradient here and the gradient there should be the same. They should be equal gradient because they've got this. They're now doing the same speed. Same thing here, equal gradient. So it goes a little bit past there and rolls off to this being flat at the top. From there to here, we're actually copying this part of the graph back to here. And I want that to come to about, so that's a bit steep, that bit. Comes off down to something like that, and then there's a similar shape here. Final part, slowing. Now, because these two have the same slope but negative sign, it's a copy of this curve coming back the other way. And it should sort of curl around. Now, the value it should come back to here is this 1.95. That's the end there. Top up here is 3.3, where it went to. This distance here was 1.2 kilometres at the same speed, and this bit was 0.9 kilometres that it drew at the end. And to check the graph, I got Desmos to create the calculation for me. And we got the right shape. And if you look at this, it's just underneath there, that's up at 3.3. A straight line between here and here, that's about 0.9. The graph is completed. So that's a fairly complicated question, building up, adding information to a graph so you can do the sketches as you go through. Okay, so hopefully you now got all the skills you need.